When sizing the ground conductor for each pipe using the tap rule, firstly determine the allowable ampacity of the 350 kc mil THHN copper conductors. Using the 75 degrees Celsius rating and table 310.15b16, the ampacity is 330 amps. Secondly, multiply the ampacity by the tap rule length factor. This calculation is 330 amps multiplied by 25 feet divided by 3 feet, which equals 2750 amps. Thirdly, divide the total ampacity by the number of pipes, which is 2. So 2750 amps divided by 2 equals 1375 amps. Then use table 250.122 to select the appropriate ground conductor size. For 1375 amps, a 250 kc mil copper conductor is suitable. Now, regarding the conductor size requirement, the 350 kc mil THHN copper conductors are indeed too small to meet the requirements of 240.21 B2. The breaker lugs are rated for 75 degrees Celsius, and the ampacity of a 350 kc mil conductor at 75 degrees Celsius is 330 amps. This is less than the 400 amp fuse rating. To correct this issue, consider these options. 1. Replace the 350 kc mil conductors with 500 kc mil conductors. This size conductor has an ampacity of 400 amps at 75 degrees Celsius, which meets the fuse rating. 2. Install a current limiting fuse in the tap conductors. This will reduce the maximum current that can flow through the conductors, allowing the use of 350 kc mil conductors. 3. Use a separate 250 kc mil copper conductor for the ground connection in each pipe. This ensures that the ground conductors meet the requirements of the tap rule, even though the phase conductors are undersized. Let's delve deeper into understanding the tap rule and its implications for the specific scenario. The tap rule, as outlined in NEC 240.21 B2, allows for tapping conductors from a larger feeder under specific conditions to supply a smaller load. These conditions are designed to ensure the safety and protection of the conductors. Key considerations include the length of the tap conductors, their ampacity relative to the overcurrent protection device of the feeder, and proper overcurrent protection at the tap's termination point. In this case, with a 25-foot tap, the tap conductors must have an ampacity of at least 1/3 of the overcurrent protection device protecting the feeder, which is the 2000 amp service. The tap conductors are feeding a 400 amp disconnect, meaning the initial conductor size chosen 350 kc mil THHN falls short of the required ampacity to handle the intended load safely and within code compliance. Furthermore, the ground conductor sizing is crucial for providing a safe path for fault current to return to the source, enabling the overcurrent protection device to trip and clear the fault. Incorrectly sized ground conductors can lead to elevated touch potentials, equipment damage, and increased risk of electrical shock. NEC Table 250.122 is specifically used to determine the minimum size of equipment grounding conductors based on the rating or setting of the overcurrent protective device in the circuit ahead of the equipment. When applying the tap rule, it is essential to consider the adjusted ampacity requirements introduced by the tap and ensure that the ground conductor is appropriately sized to handle the potential fault current associated with the tap. In this instance, calculating the adjusted ampacity based on the tap rule leads to the determination that a 250 kc mil copper conductor is required for the ground, ensuring adequate fault current carrying capability. Now let's elaborate on the options available to address the undersized conductors. The first option involves replacing the 350 kc mil conductors with 500 kc mil conductors. As mentioned, 500 kc mil THHN conductors, when rated at 75 degrees Celsius, have an ampacity of 400 amps, which matches the rating of the fuses in the 400 amp disconnect. This solution ensures that the conductors are adequately sized to carry the intended load without exceeding their ampacity rating, aligning with the fundamental principle of conductor protection outlined in the NEC. The second option involves installing current limiting fuses in the tap conductors. Current limiting fuses are designed to interrupt fault currents very quickly, limiting the let-through energy and reducing the potential for damage to downstream equipment. By using current limiting fuses with a rating suitable for the 350 kc mil conductors, the maximum current that can flow through the conductors during a fault is limited, effectively protecting them from overcurrent conditions. This approach allows for the continued use of the 350 kc mil conductors while ensuring compliance with the overcurrent protection requirements of the NEC. The third option focuses specifically on the grounding system and involves using a separate 250 kc mil copper conductor for the ground connection in each pipe. This approach addresses the potential inadequacy of the initial ground conductor size in relation to the adjusted ampacity requirements of the tap rule. By providing a dedicated 250 kc mil ground conductor for each pipe, the system ensures that there is sufficient capacity to safely carry fault current back to the source, facilitating the prompt operation of the overcurrent protection device in the event of a ground fault. This approach is particularly relevant when the phase conductors are close to their ampacity limit, as it provides an extra margin of safety in the grounding system. In summary, ensuring compliance with the NEC, particularly the tap rule and conductor sizing requirements, is paramount for electrical safety and reliability. Proper sizing of both phase conductors and ground conductors is essential for preventing overcurrent conditions, minimizing the risk of electrical shock, and ensuring the safe and effective operation of electrical systems. By carefully considering the ampacity ratings of conductors, the characteristics of overcurrent protection devices, and the specific requirements of the tap rule, electrical contractors can design and install systems that meet the highest standards of safety and performance. Furthermore, remember that electrical codes and standards are continuously updated, so staying informed about the latest revisions and interpretations is crucial for maintaining code compliance and ensuring the safety of electrical installations. Consulting with qualified electrical engineers and inspectors can provide valuable insights and guidance on complex electrical design and installation projects. Consider the practical implications of these calculations and code requirements. In a real-world scenario, factors such as ambient temperature, conductor bundling, and voltage drop can further influence conductor ampacity and the overall performance of the electrical system. Therefore, it is essential to account for these factors during the design and installation phases to ensure that the system operates within its intended parameters. Ambient temperature affects the heat dissipation capability of conductors, and higher ambient temperatures can reduce their ampacity. Conductor bundling, where multiple conductors are grouped together, can also reduce ampacity due to reduced heat dissipation. Voltage drop, which is the reduction in voltage along the length of a conductor, can affect the performance of equipment connected to the circuit. To address these issues, directing factors are often applied to conductor ampacity based on ambient temperature and conductor bundling, and conductor sizes are selected to minimize voltage drop within acceptable limits. Moreover, proper installation practices are essential for ensuring the long-term reliability of electrical systems. This includes using appropriate connectors and terminations, providing adequate support for conductors, and protecting conductors from physical damage and environmental factors. Regular inspections and maintenance can also help identify and address potential issues before they lead to more significant problems. In addition to the technical aspects of conductor sizing and grounding, it is also important to consider the economic implications of different design choices. Using larger conductors or current limiting fuses may increase the initial cost of the installation, but it can also reduce the risk of equipment damage and downtime, leading to long-term cost savings. Therefore, it is essential to weigh the costs and benefits of different design options to make informed decisions that optimize both safety and economic performance. Consider the broader context of the electrical system and its interaction with other building systems. Electrical systems are often integrated with other systems such as HVAC, lighting, and fire alarm systems, and their performance can be affected by these interactions. Therefore, it is important to consider the overall system design and ensure that all components are compatible and coordinated. For example, the selection of lighting fixtures can affect the overall energy consumption of the building, and the design of the fire alarm system must be coordinated with the electrical system to ensure that it operates reliably during a power outage. Collaboration between different trades and disciplines is essential for achieving a well-integrated and high-performing building system. To further enhance understanding of the concepts discussed, let's explore some specific examples of how the tap rule is applied in different scenarios. Firstly, consider a situation where a tap is made to supply a motor control center. In this case, the tap conductors must be sized to carry the full load current of the motor control center, and the overcurrent protection device at the tap's termination point must be sized to protect the conductors and the motor control center. The tap rule allows for some flexibility in conductor sizing, but it is essential to ensure that the conductors are adequately protected from overcurrent conditions. Secondly, consider a situation where a tap is made to supply a panel board. In this case, the tap conductors must be sized to carry the load served by the panel board, and the overcurrent protection device at the tap's termination point must be sized to protect the conductors and the panel board. The tap rule also allows for the use of current-limiting overcurrent protection devices to reduce the potential for damage during a fault. Thirdly, consider a situation where a tap is made to supply a single piece of equipment. In this case, the tap conductors must be sized to carry the load of the equipment, and the overcurrent protection device at the tap's termination point must be sized to protect the conductors and the equipment. The tap rule also allows for the use of flexible cords and cables for connecting equipment to the tap point, provided that they are properly sized and protected. In addition to these specific examples, it is also important to consider the general principles of electrical safety and code compliance. This includes following proper grounding techniques, using approved materials and equipment, and performing regular inspections and maintenance. By adhering to these principles, electrical contractors can ensure that electrical systems are installed and maintained in a safe and reliable manner. Remember to continuously update your knowledge of the NEC and other relevant standards and regulations. The electrical industry is constantly evolving, and new technologies and practices are being developed all the time. By staying informed about the latest developments, electrical contractors can provide their customers with the best possible service and ensure that their electrical systems are safe and efficient. Consider attending industry conferences, taking continuing education courses, and subscribing to relevant publications to stay up to date on the latest trends and best practices. Moreover, consider engaging with professional organizations and trade associations to network with other professionals in the field and share knowledge and experiences. These organizations often provide valuable resources and support for electrical contractors, including training programs, technical assistance, and advocacy efforts. By actively participating in the electrical industry, electrical contractors can contribute to the advancement of the profession and help ensure the safety and reliability of electrical systems for the benefit of society. Think about the long-term implications of your design and installation choices. Electrical systems are expected to last for many years, and their performance can have a significant impact on the environment and the economy. Therefore, it is important to consider the life cycle costs of different design options and choose solutions that are both environmentally friendly and economically sustainable. This includes using energy-efficient equipment, minimizing waste, and recycling materials whenever possible. It also includes designing systems that are easy to maintain and upgrade, so that they can continue to meet the needs of the building over time. By taking a long-term perspective, electrical contractors can help create a more sustainable future for all. And finally, always prioritize safety in all aspects of your work. Electrical work can be dangerous, and it is essential to take precautions to protect yourself and others from harm. This includes wearing appropriate personal protective equipment, following safe work practices, and being aware of potential hazards. It also includes communicating effectively with your colleagues and supervisors to ensure that everyone is working together safely. By making safety a top priority, electrical contractors can prevent accidents and injuries and create a safer work environment for everyone.